The topic of this video is Uncertainty principle for non-commuting operators. Let us take a quantum system with a state function ket psi, and let us take two physical quantities of the system as A and B. And in quantum mechanics, they'll be taken as Hermitian operators. That means if you take their daggers, A dagger, that will be equal to A, and then the B dagger, it will be equal to B, where the dagger operation is Hermitian conjugate operation. Expectation value of operator A is equal to this bracket of psi A and psi, and it will be real quantity because the eigenvalues of Hermitian operator A, they are real numbers. That means if you do a dagger operation for this bracket A, you will get the same number. Similarly, we get the same kind of expression for even the operator B. So if we consider the dagger operators on A minus bracket A and B minus bracket B, then you can say that even they are also Hermitian operators. The deviation of deviation operators delta A and delta B, they can be defined as A minus bracket A and then B minus bracket B, and their squares can be written like this. And now we try to calculate the expectation value of delta A squared, and that you can do with the definition of your expectation value as this psi delta A squared and psi, and here you can substitute for delta A squared, and then you can write this as A minus delta A into A minus delta A, I'm sorry, A minus bracket A into A minus bracket A, and then we can write this thing as it's a dagger because it's a Hermitian operator. And then by using the properties that if an operator acts on ket, then we can take that operator inside the ket, and then if an operator's dagger acts on a bra, then we can take that inside without the dagger and write that thing as a bra vector. So here we can write this, we can take this dagger operator inside this and write this thing as bra, I mean A minus bracket A into psi, and then A minus bracket A into psi. And in the next step, we call this A minus bracket A into psi as some other ket vector, which is F, ket F. Then if we call that way, then we can write this expectation value of delta A squared is equal to bracket of FF, and we call this as equation number 1. Similarly, for your operator B, we can define a ket vector G such that it is equal to ket B minus bracket B into psi. Then we can write this expectation value of delta B squared is equals to bracket of G and G, and we can call that as equation number 2. Next, we can actually consider the squads inequality for vectors f and g, and that we can write as this fg bracket modulus square is less than or equal to bracket ff into bracket gg. And in case you are worrying how we are getting these squares inequality, in our earlier classes we used to define the scalar product of a and b vectors as modulus of ab into cosine theta, and if you take the modulus square of this, we can square these things up, and then since this cos square theta is always less than or equal to 1, then we can write this a dot b modulus square is less than or equal to a dot a into b dot b, and in Dirac's notation we can express even this like these brackets. So the squares inequality for these vectors f and g can be written in as this equation number 3. If you call this bracket fg as some complex number z, then we know that its modulus square is equals to the real part square plus imaginary part square of that complex number, and then it's always greater than or equal to imaginary part of z squared. And for a complex number z, which is defined as real part of z plus I into imaginary part of z, z star, the complex conjugate, is equals to real part minus I into imaginary part. So we can write the imaginary part as z minus z star over 2I. So here we can actually write down this as 1 by 2I into z minus z star whole squared. Since z was bracket fg, z star will become bracket of gf. So we can write down the squares inequality in terms of fg's like this, and we can call this as equation number 4. And if you try to calculate this bracket of fg, we can write down the expression for f and the expression for g from those equations number 1 and 2, and then we can when we take this a minus bracket a to the front, then it will become a minus a dagger a minus bracket a old dagger, and then this, when it comes front, it will become as it is. So since it's the dagger is itself, we can write this thing as a minus bracket a into b minus bracket b, and when we do the multiplication, we get ab minus a into b bracket b, and then minus bracket a into b, and then minus bracket a into bracket b, and then we can separate these psi Brassai and Ketsai acting on and all these terms into these 4 terms, and when we do that, we can actually see that it is giving us expression value of a into b minus expression value of a into expression value of b, and similar kind of terms. And we can see that here it should have been plus sign here and here, so this and these terms will get cancelled. We can write down the bracket of fg is equals to your expression value of a into b minus expression value of a into expression value of b, and we can call this as equation number 5. Similarly, we can write down the bracket for gf, and it will become ba minus ab as equation number 6. So the equation number 4 that we had for square inequality for vectors f and g can turn into this equation number 7. And from equation number 1 and 2, if you substitute the values of f bracket f and bracket g and g, then we can see that it will be bracket of your delta a squared into bracket of delta b squared, and it's greater than or equal to this 1 over 2i, and then expression value of your commutator of AB, and that's because commutator of AB is equals to AB minus BA. So this we can call as equation number 8. And then if you consider two operators, especially the position operator x and then momentum operator px, then commutator of these is actually IH cut. So if you substitute this into this equation number 8, then we can see that these operators we get this, and then if the value of expression is delta x, and then if you're actually squared, and then if this value is delta p squared, and it's greater than or equal to h cut by 2 whole square. And if you take a square root operation on both sides, we can see that this delta x into delta p is greater than or equal to h cut by 2. And this is our famous Heisenberg's uncertainty principle. And we call this equation number 8 as the uncertainty principle for two non-commuting operators A and B. That's it in this video. Thanks for watching.